Hi, my name is Namho, and today I will be presenting my implementation for assignment 1, Eulerian video magnification. Eulerian video magnification is a powerful tool, uh, technique that we discussed in class that reveals subtle temporal variations in videos that are invisible to the naked eye. So we discussed that it can visualize blood flow under the skin and also amplify different micro movements and even detecting like breathing patterns. So an example being, we saw the face example as well as the different, the baby breathing. So in this presentation, I'll walk you through my implementation and show the results on the 3 different videos that were shared, and also discuss some of the challenges that I faced and how I solved them. So let's start by understanding the technical approach. So the Julian video magnification pipeline I implemented consists of 5 different phases. The first one, I load the video frames and convert them to BGR to RGB, then to the YIQ color space. And second, I build a Laplacian pyramid by decomposing each frame into multiple spatial frequency bands. And third, I apply temporal bandpass filtering in the frequency domain using FFT to each pyramid level. And fourth, I collapse the filtered pyramid to reconstruct the frames with the amplified signal. And lastly, I convert everything back to from YIQ to RGB to save the output. So just to go over why is it called Eulerian? So unlike the Lagrangian methods that track individual pixels or features across frames, this method observes temporal changes at fixed spatial locations. So this makes it very computationally efficient, and um, it naturally handles complex motions without requiring optical flow or feature tracking. So the key insight is that, it captures subtle temporal variations like color change from blood flow or like tiny positional changes from breathing. So these exist at specific frequency ranges. And by decomposing the video in both spatial and temporal frequency bands, we can selectively amplify only the frequencies of interest while like suppressing noise and irrelevant motions. And this is a multi-scale approach and is very essential for maintaining visual quality. So now let's dive into the actual implementation components. So let's first discuss the color transformation part. The first step is converting frames from RGB to YIQ color space, and YIQ separates the luminance information in the Y channel from chrominance information in the I and Q channel. So this separation is critical because it allows us to independently amplify intensity variations and color variations, which is crucial for like highlighting subtle changes like blood flow. And if we look at the different functions implemented, I implemented this using the matrix multiplication. So for standard, RGB to YIQ and YIQ to RGB transformation matrices. So the functions reshape the frame data to process um, the pixels efficiently, and we apply transformations using the NumPy dot product, and then reshape it back into the original dimensions. And so the functions handle both single frames and also entire video sequences using the vectorize operations. Um, I also clip the RGB output to the 0 to 1 range to handle any like numerical errors from the inverse transformations. Now, next, we can discuss how we construct the Laplacian pyramid. So to construct this, and this being very central to the approach, as discussed in class, I implemented this using a 2-stage process. First, I built the Gaussian pyramid, and this is by successfully downsampling frames, and then we start with the original frame at level 0, and then I apply Gaussian blurring um, using a 5 by 5 kernel with OpenCV's Gaussian blur here, the dot Gaussian blur function, and then downsample by a factor of 2 at each subsequent level. Next, the Gaussian blur step before downsampling is very critical for preventing aliasing artifacts that would otherwise occur during the downsampling operation. So to do this, I use the OpenCV's resize function with linear interpolation for the downsampling. So for all 3 videos that were provided, I used the 4 pyramid levels, which provided a really good balance between the computational efficiency as well as multi-scale representation. And in the second stage, I compute the Laplacian pyramid from the Gaussian pyramid by taking the difference between different adjacent levels. So if we look at the mathematical relationship, the Laplacian at level I equals the Gaussian at level I minus the upsample version of the Gaussian at, uh, the Gaussian at level I plus 1. Yep, as defined here. And this difference captures the high frequency spatial details that are lost during the downsampling process. And I think it's important to mention that the coarsest Gaussian level, which has like no adjacent coarser level for subtraction, becomes the final level of the Laplacian pyramid and serves as a low frequency residual. So this scale decomposition is powerful because different spatial frequencies can be amplified independently, and so fine pyramid levels contain very high frequency spatial details like edges and textures, while coarse levels contain low frequency information corresponding to large image structures. Now, for the core, like Eulerian magnification is temporal filtering. So for each pyramid level, I treat pixel values across frames as time series and um, convert them to the frequency domain using the FFT. So I first create a frequency array using NumPy, uh, and then so I create the frequency, yep, using NumPy, and the fifth rec function, as you can see, and we reshape the data to process all the pixels simultaneously. And the reason why we do that is so that it makes it possible to isolate the temporal frequencies linked to the phenomena like heartbeats or breathing. Now, now we can look at the mask creation. And so I perform all filtering entirely in the frequency domain for efficiency. And after applying the numpys like FFT along the time dimension, I create a bandpass filter mask that selects only the desired frequency range. So this is critical because FFT or real signals is conjugate symmetric. So I filter both positive and negative frequencies together. So you can see in line like 352, um, where I include both frequency ranges. This ensures like the inverse FFT yields real valued results uh, without imaginary components. Yeah. So once filtered, I apply the FFT to return the signal into the time domain, and this produces a signal containing only the variations within the chosen band, which I amplify by a specified factor before adding back to the original. And the key innovation here is that this is level dependent, so uh, level dependent amplification. So in the main processing loop, um, each pyramid each pyramid levels will receive amplification divided by 2 to the power to the level index. So at level 0, it gets full amplification, then level 1 gets half, level 2 gets quarter, and so on and so forth. So this actually prevents the over amplification of the coarse pyramid levels. And we discussed this in class, which would create a visible halo effects and I think natural distortions around the large image structures. Yeah. Now, after temporal filtering, I reconstruct the final frames by collapsing the pyramid. So this reconstruction process is to inverse it's the inverse of the pyramid construction. I works by iteratively combining the pyramid levels from coarse to fine resolution. So I start with the coarsest level, which is the low frequency residuals from the Gaussian pyramid, and then we progressively add back the finer Laplacian levels. So at each step, you can see I sample the current reconstruction using the OpenCV resize with linear interpolation, and this is to match the dimensions of the next final level. And then I add um, the corresponding Laplacian level to recover the high frequency details. So to just discuss the mathematical relationship here, uh, Gaussian at level I, right? Gaussian at level I, it uh, equals the Laplacian at level I plus, so it equals the Laplacian plus the upsample Gaussian at level I plus 1. So the inverse of our decomposition formula. So in a way, we are working backwards through all the pyramid levels, and then I eventually obtain um the full resolution reconstructed frames in the YIQ space. And finally, I convert them back to the RGB using the inverse color transformation. So this is all part of the reconstruction, and thus this produces the video with the amplified temporal variations. So we can discuss